All right, it's probably time we kick things off. So with that, I'd just like to say welcome to everyone who's here. My name is Josh. I manage the outreach for the Australian Research Council's Centre of Excellence in Exoticon Science. I'd like to start by acknowledging the traditional custodians of the land which I am presenting to you from, the Wurundjeri people of the Kulin Nation. And Exoticon Science recognises that Aboriginal and Torres Strait Islander people were the first scientists and pay our respects to their elders, past and present. Well, happy National Science Week to everybody. Personally, I celebrated by getting vaccinated. Thank you, science. And to kick off the Centre's celebrations, we've got a really great public lecture lined up tonight from two researchers, Professor Tim Schmidt and Dr. Jessica Alves, who will be sharing some of their research and the science behind their work as well. So very exciting. Thank you for joining us tonight. But before I hand over to them, I'd like to try something. So I know some of you have already jumped over to this and started. But if you use that QR code or go to www.menti.com and chuck in that code, I want you to give us what comes to mind when you think of light. Just a few words. I'll give you about a minute, really quick. It could be something to do with how we receive light, where we find light, maybe what we do with light. No wrong answers. So I'll give you about another 30 seconds to just submit whatever comes to mind first. Make sure that everyone can see that. All right, so if I jump over to our answers as well. All right, quite a eclectic collection here. All the way from poo to life, feather, very funny. We've got a few that are popping up more than others though, like energy and sun, beauty, warmth, rainbow, light bulb, brightness. Very nice, some great answers here. And I think that really that, jump back over. I think that really sums up what we do here at Exoticon Science quite well. For starters, we're a collaboration between 5 universities, consisting of University of Melbourne, RMIT, Monash University, UNSW, and UCID. And we're made up of chemists, physicists, engineers, all working on technology and research to do with light, whether that's turning light into energy, so better solar, or turning it back into light like flexible displays. Some people are even working on new types of cancer treatment to do with light. So there's real variety of researchers doing different things. And I'm excited to hear about some of that research tonight. So I think without further ado, I will hand over to Jess and Tim, the actual researchers. And yeah, Tim, I think you're going to kick things off.
Yeah, I even remembered to unmute myself. So welcome everybody. I'm on Gadigal country up here in Sydney, and if you hear some noises in the background, that's the kids. Okay, so I'll share my presentation. Looks like we're there.
Just wait a bit. Yeah.
We're good?
Yeah.
Okay, so when Jess and I were preparing this talk, I mean, it evolved. We, of course, knew what we were going to talk about in broad terms. And we decided to make this a joint presentation where we mix things through. And ultimately, we end up with a a talk which would better be called Alves and Schmidt talk about glowing molecules and energy. So I hope you enjoy it nonetheless. We definitely will be talking about glowing molecules and energy, and Jess will even be showing you some glowing molecules from her kitchen, I suppose. All right, so Jess.
Hi everyone, I'm Jess. I'm a postdoctoral research at Teams Group at UNSW. I enjoy studying the effect of light on molecules and how we can manipulate it. So let's start our talk with the most abundant light source there is, which is the sun. So the sun gives us all the colors of the rainbow. However, it is not only that, there is even more than that, as Tim will tell you next.
Yes, that's right. It's very important to consider that the sun gives us not only the colors we can see, but in fact, colors on either end of the spectrum as well. We talk about there being color below red, which is called infrared. And you know about that, at least anecdotally, as heat, right? It's radiation that will warm you up. That doesn't sound too bad. And there's also energy at the other end, above violet, which we call ultraviolet, and you know that too. You know that it can be dangerous. It can cause sunburn and even skin cancer. We know about these parts of the spectrum and have known about these parts of the spectrum for about 200 years. And here's a picture on the right of Herschel demonstrating the infrared part of the spectrum. And this is a pretty nifty experiment. You can see, hopefully, he's got a prism held up to a slit on the wall, letting in daylight, and the daylight is split by the prism up into the spectrum. And he's got laid out at the red end of the spectrum a couple of thermometers, and he shows that the thermometers actually heat up where they are at the end of the spectrum, but not beside the spectrum, and therefore, or thereby, he discovered infrared light. Now, why do we say below and above? You know, like infrared. What is it that makes it below red? Well, to describe what is high and what is low in terms of the solar spectrum, we have to talk about its so-called corpuscular properties, the particle properties of light. And going back to the late 19th century, it was postulated that light was made up, well, actually, I mean, you know, even Newton postulated that light was made up of energy packets, but he didn't have a good reason for it. But scientists trying to understand the exact spectrum of glowing things like glowing metal or lava or even the sun, they needed to invoke the idea of the quantum of light, which we call a photon, an energy packet of light with an energy which is directly proportional to the frequency of the light, and therefore inversely proportional to the wavelength. So going on only 1 or 2 decades later, Einstein used this idea of the photon, the energy packet, to explain something called the photoelectric effect. And that's where it's observed that, for instance, you know, you shine light on a metal, and it's only when you get to a certain threshold short wavelength, therefore high frequency of light, that you can start to see electrons being ejected. And so the idea is that only light packets of a certain energy can make that electron eject. And this is very closely related to how solar cells work. And a lot of our research is very, very intimately linked with this idea. So how do we measure the energy of a photon? Well, we measure it in terms of a unit called the electron volt. And the electron volt is directly related. Yeah, it's the same volts that you know about on batteries, right? So you know that you can have a lithium-ion battery of about 3 volts or a AA cell of about 1.5 volts. And that voltage, if you accelerate an electron through the voltage applied by that battery, you'll end up with an energy of the electron of that number of electron volts. And this is directly related then to the color of light you can make by applying that same voltage to the right kind of substance. And we'll actually deal with this a bit later in the lecture. So if I imagine now making a plot of light out versus the voltage for, say, a red LED, I'll have a plot something like that. And then I'll need a slightly higher voltage to get green light and a higher voltage than that to get, let's say, violet light. Okay, well, that's great. But photons aren't that much fun unless you do something with them. In fact, you can only see photons because they're absorbed by molecules in your eye. And to take you through the science of that, I pass back to Jess.
Yes, so let's see what happens when light actually interacts with molecules. So I have here my dummy molecule on the left. This molecule initially is in the ground state. So it's a state where the molecule is happy to be at, and it's the lowest energy state. So as soon as the molecule interacts with a photon, it can get to an excited state. This is called absorption. And in this excited state, the molecule is not really happy about to stay there. So the molecule want to release energy and go back to the ground state. Upon the release of this excess energy, the molecule will can emit a photon in a process called fluorescence. You see on the right in the animation, there is a fluorescence molecule called fluorescein. And this molecule is just mixed with water, and as you can see, it can glow in the dark. So, but we don't need to have fancy molecules to be able to observe this behavior. So we can have actually homemade materials to see that. So let's do some kitchen chemistry. So I think, no, wait. Yeah, close. So I have, let's see. Look at that. So I have in my hand a UV torch and a gin and tonic. And we can see that the UV torch is clearly purplish, but as soon as I go to the liquid, I have blue. So if we go back to the slide, team. What happens in here was that I just had, yeah, to prove that I'm not lying, let me show you. Yeah, it's just a cup with gin and tonic and the UV light. So we had the molecule in the ground state that it was excited upon UV light. And when it excited, we saw a blue color. As Tim said, the colors have different energies, and the UV light has higher energy than the blue light. So where did the excess energy went? Well, there is some loss, and this loss was in heat. That's why we saw the blue fluorescence. Now, that's not all that can happen when light interacts with a matter. The light can also induce a change in the shape of the molecule. So we have again our molecule in the ground state. Upon light irradiation, this molecule suddenly goes to another shape called this molecule have different excited states depending on the shape of the molecule, and we can access those excited states. Those molecules are so important that they have a special name, and they're called photoswitches. So one example of photoswitch is shown in the slide. So as you can see, upon light irradiation, in a particular bond of the molecule, there is a bond rotation. It might not see much this change. However, those isomerization that we call are super important. For example, we need this for our everyday lives. So we have a molecule in our eye called the retinol, and depending on the light irradiation, this molecule will isomerize so it will change its shape to the trans retinol. Once this molecule changes the shape, it will just activate some proteins around it that will ultimately lead to a nerve cell signal that will help us interpret image. That's how we can see. So the photoswitches not only can change the shape, they can also make or break bonds. As you can see in the left, we have two examples of photoswitches where there is a bond formation. So how they look like in real life? Well, we can actually see what's going on. As you can, normally the photoswitch, it changes the color. So we can see this naked eye video of the photoswitch actually switching. So we saw how we can use how photoswitches work on a molecular level. However, we can do much more than that. We can actually manipulate photoswitches in the molecular level to make materials that can perform some action for us. For example, materials that can grab and release things upon light incentive. So in this case, they're trying to use to make based on a fly trap to actually grab things and release upon a light switch. So that's pretty cool. There are plenty of opportunity of what we can do with that. So now that we learn a bit about photoswitches, about more complex, about other complex energy systems.
Thanks, Jess. Yeah, so we've learned a little bit about molecules absorbing light and either emitting fluorescence or changing shape. Molecules, though, can get a little bit more complicated. In fact, they can have multiple excited electronic states. And a very nice example of this is chlorophyll, which is the molecule that makes trees green and makes leaves green, trees green. And why? Why is it? Why is it that leaves are green? Well, it's not because it absorbs green light, it's the opposite of that. It's because chlorophyll absorbs red light and it absorbs blue and violet light. If you look on the right-hand side of your screen, you'll see what we call an absorption spectrum, which is a graph of how strongly a molecule absorbs light. And in this case, you can see that it's absorbing strongly in the red, it does not absorb strongly in the green, and then it absorbs strongly in the blue and the violet. And in this case, that map of absorption strength is brought about because there are two excited states of chlorophyll. Let's call them excited state 1, which is accessed with red photons, and excited state 2, which is accessed with blue photons. And green photons just go straight through or get scattered by the leaf and give you a happy feeling when you see a nice green tree. Now, when a molecule is placed up there in excited state 2, you might think, well, it's going to sit there and it's going to shine light back. But actually, this is something that molecules do. And in fact, all matter will do this. If you are in a state higher than the first excited state, probably very quickly, you're going to lose that energy and you fall back down to the first excited state. That's something called Cash's law. And that means that if we shine UV light on chlorophyll, it comes back down to this lower excited state. If it emits light from there, it should be red. Now let's go back to Jess's kitchen and test that out.
Yeah, so first let me show you the materials. So I will switch the camera. So in here I have I have my plate with leaves, just the leaf that I stole from the neighbor. Don't tell him that. I have in here some nail polish. So let's try to mix them and see what happens. So if we can get some hands. So let's just mix a little bit. Sort of mixed. Now, let's see if you can see something. Let's go for my UV again. Let's try to make it. Yeah. So let me try to turn off the light. Moment. And try again. You might be able to see that it's red, as we expect by the team's theory. How cool is that? All right.
I can't exactly claim that as my theory, but
it's not your theory.
It's well known to science. And in fact, the fluorescence from chlorophyll can be used to map photosynthetic organisms in the sea using satellites in space, which is where satellites are. Okay, so launching back into the presentation, share the, give me a thumbs up when it arrives on your screen, Jess.
Give it a moment. Yeah, it's good.
Okay, so we understand a little bit more about molecules, that if they're excited to a second excited state, they'll fall back down. Now we're going to look a little bit at the electronic structure of something which is like an enormous molecule. Now you mightn't think of diamond as a molecule, but in a sense it is. It's a continuous network of carbon atoms arranged in what we call a diamond structure. I know that sounds obvious, but in fact we use that phrase diamond structure even for other things which aren't diamond. But it's a particular arrangement of the atoms, and you can see spinning around on your screen an example there. Now, why are diamonds see-through? They don't absorb visible light. If you could see in the UV, you would see a color for pure diamond, as in pure carbon diamond, right? So it takes ultraviolet light to promote a diamond from its ground state to its excited state. And there are, in fact, so many densely packed excited states in a material like that, that I'm not going to draw it as a discrete unit, but just as a band of states. Now, that's all well and good, but we don't tend to make electronic devices out of diamonds, at least not pure carbon diamonds. But if we take a walk down the periodic table, there's carbon. And if you walk down to silicon, we see the situation change. Silicon is arranged in the same way as the carbon atoms in diamond, but in this case, the first excited state of that material lies only 1.1 electron volts up. And that's actually in the infrared. So silicon will absorb all wavelengths throughout the visible, which makes it very useful if you want to absorb light. And in fact, that's why it looks black. Why is it shiny? Well, that's another property which we won't go into. But if you can make this 200 microns thin, and it blocks nearly all of the light and only lets through light below about 1.1 electron volts. And it does fluoresce. In fact, scientists use the fluorescence from silicon to diagnose whether or not a solar cell is going to be good or not. So they have these laid out in the factory, and you can take photographs in the infrared of the fluorescence and determine if something is a defect or not. Okay, so I've got a video now to show you, because there's something about what happens inside a material like silicon when it absorbs light that I want you to understand. I just have to make sure I can share. I'm sharing my sound. I hope this isn't too loud for you. It's a video I prepared about 2 years ago. It's about what is an exciton. We're actually going to dive inside a diamond. If you find this extremely cheesy, oh, my elbow hit my mouse. I'm so sorry. I have to dive in again. I won't get so excited this time. So we're looking at the arrangement of carbon atoms. There's a lot of electrons in there. We hit it up with light. One of those electrons is going to be excited, and it's going to orbit around a bubble where it needs to be, which we call a hole. So here's the electron and the hole orbiting each other. By the way, this inspires the logo of the center, which you see at the top right of the screen. It also stands for Sydney and Melbourne. So that's an exciton. The exciton is a quantum of excitation in matter. So once we have this quantum of excitation created by light, we can do all sorts of things with it. So if you create an exciton when light's absorbed, they can emit light back. So that's behaving the same way as in a molecule. Or you can break that exciton up into the hole and the electron and make it do electrical work. So you can make electricity with excitons. You can do the opposite of that. You can take electrons and holes and inject them into a material to make an exciton and then emit light. And that's how we make LEDs. So all of these materials are intimately related. Now, if we take a material, again, it's like silicon, but you take a walk to the right on the periodic table, a walk to the left, walk up, a walk down. You can make materials which balance out, sort of like on average, they're like silicon, but they're actually, the properties are beautifully tunable. And if you mix indium, gallium, and nitrogen in the right way, you bring about a material that you can tune the gap between the ground state and the excited state, and you can make LEDs of all different colors. But a very important invention is the blue LED, because the blue LED can be used to pump what's called a phosphor. The phosphor, again, it behaves like the molecules. It absorbs the blue light and it degrades that light down the spectrum. You can always take a photon and shift it towards the red, towards lower energy in the spectrum. And in this case, that phosphor emits green and red light, and some of the blue light that comes through, then it all mixes in your eyes and you see it as white light. And so that white LED comes about from a blue LED, and that gives us the very energy efficient lighting that we're all using these days, and that it doesn't produce that the copious amounts of useless infrared light that do nothing but heat up your room. So if you want energy efficient lighting, then you want to use LEDs. Now, solar cells. As I mentioned, silicon will only absorb light above about 1.1 electron volts. But once we're above that, you know, the engineers, and a lot of this early work was done at the University of New South Wales. Once you're above about 1.1 electron volts, the quantum efficiency, so that the usage of those photons, maybe not in terms of its energy, but in terms of do you get an electron and hole out of your device, it goes very high, right up near 100%. So that's all well and good, but the spectrum from the sun doesn't fit all snugly between 1.1 electron volts and 3 electron volts, right? We get, as Jess said at the beginning, okay, not only all the colors of the rainbow, but we get an even bigger spectrum than that. We get ultraviolet light and we get infrared light from the sun. And if I plot the spectral intensity versus the wavelength from the sun, you can see, yes, it peaks in the visible region, and that's probably why humans evolved to see in that region. But there's a huge amount that extends out into the infrared. Now, one of the challenges that's we've taken up in our center is figuring out how to use the solar spectrum more efficiently. So it turns out only a fraction of the sun's energy can actually be used by the very best solar cells. And this is not a fault of the engineers that have developed these cells. It's just through the fundamental operating principles, which you already understand, and I'll show you. We've gone through these principles in molecules and we've shown you them, but now you'll see how they apply to solar cells. So in order for a solar cell to make an exciton and therefore make electricity, it needs to absorb the light. And you've seen that silicon will only absorb above about 1.1 electron volts. And so everything below that in energy is gone. And there's another effect which I'll get to in a bit, which explains why we lose some of the energy above that. But all that's remaining here is this 30% of the solar spectrum down here. Okay, so as I mentioned, a molecule cannot access the excited state if the photon energy is below a certain amount. And so that corresponds to this large amount of energy out here in the infrared. Wouldn't it be great if we could upgrade that light? If we could take this infrared light and somehow convert it into useful, visible, and near-infrared light. How do we do that? How do we upgrade light? Well, the way that we're working on this in our center is to basically glue photons together. The very first step is to take a material which will absorb the photons. So in this case, my red balls are red photons, which are standing for low energy photons. They are absorbed by molecules, placing those molecules in an excited state. Now, normally that's just going to shine right back at us. But what we do, we have a little trick here. We flip a spin and trap it in what's called a triplet state. And Jess is going to go into more detail in this in a moment. And that triplet energy can then be transferred to another sort of molecule. And then those molecules in the triplets can meet and somehow put one of those in a proper emissive excited state, but using the energy which originated in two red photons to bring about, in this case, a blue photon. Can it work? Does it work? Has anyone done it? What do you reckon? Of course. These are photographs from, actually two of these photos are from my lab, and one is from Wallace Wong's lab at the University of Melbourne. And if I'd asked him, instead of just taking this picture from another presentation, I would have got a higher quality image. Nevertheless, you can see that using molecules, we're highly adaptable here. We can turn red light into blue light, we can turn green into blue, we can turn red into yellow. And in all of these cases, we're moving a light source up in terms of photon energy. But because we always have to use two photons to produce one, we don't break any laws of physics. And in any case, if we'd broken laws of physics to do this, you'd just have to rewrite the laws of physics because we actually did it. Right? But there's nothing spooky here. It's all explainable. Jess is going to explain in more detail.
All right. So let's see a bit about the energy of those states. So we have the molecules that absorb the light initially, and that we call the sensitizers. So in this scheme, we have two sensitizers. They're equal, just two molecules, and they both get excited upon the absorption of a photon to the singlet excited state. then they will go to the triplet excited state, which has a lower energy than the singlet excited state. From this triplet, they will then be transferred to the triplet of an emitter. Now I have then two molecules that are in the triplet excited state, two emitters, and those two emitters can then perform triplet annihilation, causing then one emitter to go to the singlet state and the other emitter to go to the ground state. This emitter in the excited state can then go to the ground state, emitting a photon. Now, why up conversion? Well, because the photon that is emitted from this emitter is much higher energy than the incoming photon that causes the excitation of the sensitizer. All right, now Tim will tell you a bit about how does this work in practice.
Yeah, well, I could talk for hours about this process. We've been researching it for many years, but I wanted to show you just a very exciting result from our recent work, where we performed this photochemical upconversion from below the energy threshold of silicon for the first time. And this was published in Nature Photonics last year. And to do that, we actually used a very special type of, it's kind of like a supermolecule to do the original absorption. So in this case, it's a lead sulfide, so-called quantum dot or semiconductor nanocrystal. And the absorption of that material is shown over on the right as a dashed line. And we excite that just below the absorption threshold of silicon. And what we know is that it transfers energy to these molecules. Not sure if you can see my cursor. I guess you can't.
We can.
You can. So this one in the middle is called tetracene. It's called TIPS, tetracene carboxylic acid. And it sticks onto these quantum dots through the little carboxylic acid group hanging off the butt here. It's sort of, imagine it turning around and grabbing hold of the surface using its carboxylic acid group. And it transfers, so that the quantum dot transfers energy to this ligand, and the ligand transfers energy to these alien-looking molecules. I love this molecule, V79. Look at it. It looks like straight out of Space Invaders or the Church of the Flying Spaghetti Monster. In fact, it's pretty much like the Flying Spaghetti guy. Anyway, this molecule, V79, can accept the triplet energy from the tetracene carboxylic acid, and then these guys undergo annihilation to bring about emission way up here. I say way up. This is on the edge of the visible spectrum, but compared to where the absorption was, right, this is huge. If you really want to go chest beating about how many nanometers of upconversion, well, look, it's hundreds, many hundreds. But what matters is that we got underneath the absorption threshold of silicon. And in this experiment, we actually used a silicon wafer to filter the excitation light, just to prove that silicon was not absorbing our excitation light. And then we performed the upconversion and detect the light using a silicon detector. So that was very exciting, and we're working hard. And hopefully Jess is going to push this over the next couple of years. Right. So the next big effect here is to talk about is not the below threshold problem, but the fact that if you excite a material like silicon well above its absorption threshold, it rapidly loses that energy and comes crashing back down and to the first excited state, if you like, losing all of that excess energy as heat. You saw that happen in chlorophyll, and it happens in silicon solar cells. And because of that, it means that the proportion of a photon energy that's harvested by a solar cell goes down as you go up in terms of the photon energy. And so whereas near the band gap, you use the energy quite well, as you go higher and higher, you have a diminishing proportion that you're harvesting, and that leaves us only with this 30% down here. So in order to address that, well, what we do is we think, well, what if we could split the energy of photons in two? So if you are twice the energy threshold, can you split that photon energy into 2 bits and harvest it separately? And the answer is, we think so. We and a couple of other labs around the world are working hard on this. I mean, these are big hitting labs at MIT and Cambridge, and this is what we're trying to do. So we take a material, in this case it's called tetracene, it's like 4 benzene rings in a row, and it undergoes the opposite process to what you saw before, where we join triplet energies together into a singlet. In this case it runs backwards, where we take one singlet and split it into 2 triplets. But when we do that, the idea is that those 2 triplet packets can then be harvested by silicon and produce 2 electron hole pairs. If you can do that efficiently, and a sort of idea for how to do this is drawn in the device below, that means that your EQE curve, that's the external quantum efficiency curve, in gray here on the right is what we expect for the very best silicon cells. If we can put singlet fission on top of the cell and make it work well, then we may well get something like this in yellow, where once you get to twice the band gap energy, you can get up to, let's say, 200% quantum efficiency, where each photon is producing 2 electron hole pairs. That would be amazing. That's the future, people. Now, Jess is going to talk a little bit more about photoswitches and how they can be related to the triplet annihilation and upconversion that I've already, and we already spoke about. Jess. I've lost Jess, or have I lost me? Are you there?
All right.
Okay, great.
Yes, I am. Oh, yeah, perfect. All right. So we learned a lot of things today. We learned about the molecules in more fundamental part, the photoswitches, the TTA. So now we're going to try to connect all the dots. So the point is, how can we use photoswitches to do TTA? Well, there is this sensitizer that we can use. For example, this palladium sensitizer. It's possible to get the emitter called body, and then we can couple this emitter with a photoswitch. So in this case, it is a DTE. This photoswitch has a ring closure upon light irradiation. Therefore, we can then make a switchable emitter. So the difference between the open and closed form are shown, highlighted in the figures. So if you go to the next slide. So we have the structure in here. So upon light irradiation with 635 nanometers, we can activate the sensitizer and activate the body P. Therefore, the body P then does the TTA up conversion. When the 254 nanometer is on, the ring, the DT then gets a ring closure, and this ring closure causes a short circuit in the system. So it effectively quenches the TTA of the body P. So then the system doesn't work anymore. So which means that we just got a way of controlling TTA with the photoswitch with light irradiation, which is pretty cool. Another idea of how we can use photoswitches is one problem that you may have thought about of having the TTA is that the molecules need 2 molecules that are excited in the triplet state. They need to be in close proximity in a short period of time to effectively annihilate. So that's not a very easy task. And therefore, one way to use photoswitch could be to help aggregate those emitters as as the photo switches can have different polarity properties. So for example, when we irradiate with light, we can have a micelle formed, and when after some time or after irradiating with another light, then we can have this micelle to be deactivated. If you want to know more about this part, you have to stay tuned in Tim's work. All right, so another challenge of solar cell research is how to have power at night. So one way to envision that is to find a way for storage, to store the excess energy that was not used during the day, and to use that energy in the night. So if we can then use photo switches for this process. So for example, I have this NBD, which is a low energy molecule that isomerizes upon light irradiation to this QC, which has higher energy. And this energy, of course, it's stored in the bonds of the molecule. So when this molecule is heated a little bit, this molecule can release a large amount of heat and return to its initial form. So this work is very interesting, and the energy can be stored for up to 50 days. A similar research also shows that another type of photo switch could be used for this energy storage. So in this work, there is this glass on the top, the first layer, where it filters the light, so to the solar field, the second layer. This solar field is a photo switch that works by having the same as previously. The difference in bonding causes energy released upon switching. And so the light goes to the second layer, and this photo switch gets some energy from it, but it doesn't absorb everything. So they coupled with a sensitizer emitter system on the third layer to provide extra photons to the solar field and increase the solar field efficiency for storage. As we can see on the graph on the right, we have that with this TTA layer on the bottom, comprising of the sensitizer and emitter, we have a higher conversion, which means more storage in this solar field. All right, so we're getting to the end of our topic, but Tim's going to tell you one more challenge and the strategy in solar cells.
Yeah, so just one or two more slides, just to tell you about something else that we're working on in the center. And that's, we're working on a bunch of technologies where we want to selectively absorb part of the solar spectrum and make electricity with it while allowing the rest of the spectrum to pass through. And the way to do that, well, let me first say that if you can do that, you can actually incorporate, there's some noise, I think. You can incorporate solar energy into architectural structures in a subjectively beautiful way, let's say. Some people will like it, some will not. Now, the way that we do this is create something called the luminescent solar concentrator. And in an LSC, you take a slab of material embedded with fluorescent molecules, and you know what they do when they absorb light, they emit light. But when molecules inside a slab of plastic emit light in all directions, only some of it can escape. The rest of it undergoes what's called total internal reflection, and is wave guided. It's a technical term. The light is wave guided through the structure in the same way that light is guided through an optical fiber. This is how the NBN was meant to work, right? At least fiber to the node. The fiber part light is bouncing around inside the optical fiber. And in this case, we've got light bouncing around inside our waveguide. And what we do is we then put solar cells at the edge in order to harvest that light. So there's a picture of that going on down the bottom here. And on the next slide, you can see some of the world-beating LSCs for harvesting green light are created at the University of Melbourne. In fact, it's probably some sort of Parkville scene in the background. And you can see in transmission, obviously part of the solar spectrum is taken out. And if you look at the whitest part of the background, the pink color hints strongly that it's green light that's being absorbed. Now, if green light is absorbed, we know it can fluoresce to longer wavelengths. That means to yellow and red light. And you can see the yellow light actually being squeezed out the side. So you see that very bright luminescent edge. That's the wave-guided fluorescence coming out the edge of this slab of plastic. Now, it's not just any old plastic. The molecules in that plastic, you know, there's only maybe 10 to the 4 of those molecules in the whole universe. Who knows? But they're all made by Wallace Wong at the University of Melbourne. That's the end of our presentation. All we want to say now is to look at this plot. If you go to a solar cell research talk, they always show this. One person gets to show this at the start of the conference. This is the plot of research solar cell efficiencies versus time. And in fact, you can see all of the work done by Martin Green throughout the 80s and 90s on silicon cells. UNSW is very prominent. There's all sorts of different solar cells that are used in space that have multi-junctions, very fancy things. But one thing's for certain, yeah, everything is going up. The future is bright. Thank you all. We have a photograph of the center. This was our first meeting back in 2018. And I think we met like one more time or something before we had no more face-to-face meetings. All very sad. Anyway, you all want to go have your dinner. These are our universities. We're sponsored by the Australian government. Thank you all.
Thank you.
Awesome. Thank you very much, Tim and Jess. We probably have time for a few quick questions if anyone has them. So you can use the Q&A button to ask those. But as someone who doesn't have a background in this stuff, I do really appreciate you starting from, you know, the fundamentals and going all the way through. And Jess, well done coming up with those demonstrations in your kitchen during lockdown. Very impressive.
It's not even really your kitchen, is it, Jess?
It's not even that.
Jessica's parked in Port Macquarie. She didn't dare to re-enter Sydney. But now we're all locked down.
Yeah, that's fair. A lot, yeah, and you know, a lot of us are. Let's have a look if we've got any questions. No, just a lot of praise, really. So, well done. Oh, yeah, we do have one. This one is from Nikki. Nikki asks, when did researchers begin working on photoswitches, molecular machines, and what are the biggest or most interesting challenges in this area or field of research?
All right, so I think I can pitch in this question. So photoswitches are known actually for quite a while. I'm not sure how long. I would say maybe the 70s or something. I mean, they were observed for a long time, but not really explained so well until the 70s, I would say. And the problem about photoswitches is that there's always this reversibility problem, that it's quite hard to find a photoswitch that never degrades. So it can limit the applications depending on what we are using. So it is definitely something that people are actively working at the moment. Also, since photoswitches, they change their properties. So one photoswitch can be very polar, the other photoswitch can be very apolar. Sometimes it's very hard to find the environment that we are going to work with. because it has to be an environment that the molecule adapts sort of well with those, even being very different. So yeah, those are, I think, the main challenges in photoswitches.
Cool. We've got another question that's come through. This one's from Andrea. Do you happen to have any current data about how much a photoswitch costs for a CubeSat to go into space that Wallace Wong and your team make? So I guess implementing them, yeah, CubeSats and small satellites, what would that look like?
Tim?
In terms of cost, I mean, the thing is that research chemicals are really expensive because you've got to pay someone to make them. So it's like, you know, you're talking $10,000 a gram or something, just because it takes someone many weeks to put everything together. But if you have an industrial process, it comes down to dollars per kilogram sort of range. So, you know, if we come up with something that demands an industrial level of production, then it can be made for really cheaply. But anything that's at the research scale literally costs, you know, thousands and thousands of dollars per gram. But that's not the intrinsic cost. It's just because you really need a specialist PhD dedicated to making it in glassware, just like in the movies, rather than in a factory.
So pretty expensive now, but hopefully not forever. We've got another question here, this one on LSCs from Amy. What would the LSCs on a building mean for natural indoor lights? For example, what would it look like from the inside?
Yeah, so what you can do, if you're worried about it looking like a pink or magenta light inside the room, you can have that if you want. But there are the materials that absorb throughout the whole solar spectrum will give you a neutral tone. So you can actually make LSCs. Whoa, kids are getting very cranky. You can make LSCs that absorb neutrally across the spectrum, so it doesn't have to look colorful like the pictures that were shown. And there's an Australian company called Clearview, which is actually using semiconductor nanocrystals to absorb light across the solar spectrum, and their products just look neutrally toned. So you couldn't tell the difference really between that and the window tint, you know, a neutral window tint.
Those solar window technology is very exciting. I think we'll go with one more question. This one looks like a nice one to end on. It's from Meg, and Meg asks, which of the innovations you work on makes you the most excited for future implementation?
Well, I guess we should answer this one each. Jess, you first.
Oh my God. Well, so I do think that photoswitches can have a huge impact in technology in general. So I do more fundamental research, I would say. However, if when we start understanding better how those molecules work and their limitations and what they're good at, and we can develop and we can overcome their limitations by the development of new photoswitches, I think it is very exciting that we can use them for a whole bunch of different areas. So for example, there is a lead on using photoswitches for phototherapy. So for example, we photo targeting of medicine, so inside of our body, for example, then we can know exactly where the medicine will be released in whatever organ we are targeting. So those are pretty exciting. So yeah, there's lots of cool research that can be done.
Yeah, so I mean, actually, I really do like photoswitches and they excite me. But in terms of what I spoke about, I'm really excited about singlet fission solar cells. it's been a while since these ideas have come up, and steadily we're getting closer and closer to solving the problems which involve interfacing organic type materials with silicon. So it's you know, two completely different paradigms and two different types of Exciton, and bridging that world is what currently really excites me. And I think there's a huge number of applications that can be brought about if you can effectively interface the organic and the inorganic worlds. Yeah, look, we've got a big wish list of things that we want to do, and thankfully we've got funding at the moment. So watch this space.
Awesome. Right before we go, I will just also plug our next public lecture, which is happening this Friday. We've got another speaker from our center and also a speaker from ANSTO. And this one is on, I guess, some work we ended up doing to produce magnetic nanoparticles for COVID test kits, because there was a demand. The Australian government was looking for people to produce these. And yeah, with the help of ANSTO's synchrotron, we were able to actually start manufacturing some of those parts. So very different topic, but still something cool the center has been working on. But I guess that's it. Thank you very much for coming along. A big thank you to Tim and Jess for jumping in there and sharing all of their research, especially considering that, this was quite a last minute digital pivot. So yeah, thank you very much, Tim and Jess. I hope everyone has a fantastic evening, a fantastic National Science Week, and hopefully we'll talk to you soon. See you, everybody.